of it. Oh, actually, I didn't hit record on that either, so. Well, it's a crappy recording from Zoom. But let's pretend.
I'm like, we got all that.
I'm hitting record, and it's ignoring me. Here we go, record to the cloud, why not? All right. Who knows how much got missed?
Probably not much.
You know, it's all just Coulom's law. I think I've answered your question, Raphael, at least hopefully enough to recognize it. It's probably not worth going through the long, dirty version of it. You'll get it in Calc 3. If you don't get it in Calc 3, then just at the end demand your money back.
I don't think I got it in Calc 3.
Demand your money back.
Think now it's too late or?
Probably. You can try it. They'll look at you strangely. All right, other questions? All right. All right, so I have a DC power supply. I assume I've gone into the power cell versus power supply or battery bit. Okay. This is the symbol I use for a battery, a DC battery, DC power supply. For the purists, they would look at this and they would just shake their heads in pity at me. Officially, that's a power cell, a battery would be more than one of them, so a battery should be, you know, however many you want to place there. I typically just do one of them. Just recognize it. I've had one student over the past who seemed to take exception, but he dealt with it. So.
Oh, no.
What am I doing? What if I went this way? All right, there we go. All right, so this is my power supply. It's a DC. Power supply.
Is it supposed to be split at the top?
Yes. So right now, this is an incomplete circuit. So if I actually set this up where I took one of the power supplies that you were playing around with last week and just attached two wires to the positive and negative side, and then had the other two wires not touching anything in particular, so it's sort of hanging out in the air, there's not a complete circuit, no current is flowing. For my power supply, this is the positive side and that's the negative side. The memory trick, the long side takes more ink than the short side, the plus side takes twice as much ink as the minus side. So the long one is positive, the short one is negative. To this, I'm going to add a capacitor. Now, the symbol used for a capacitor, at least the one that I use, are two parallel lines. They should be the same length, as opposed to the power supply, which has different ones. Now, if you look at the flash exercises, that they have other symbols of it. There's this one, and get the other one at this point. This is a polarized capacitor. We're not worried about polarized capacitors. For a polarized capacitor, it matters when you put a capacitor into the circuit, it matters which way you put it. I don't care. We're just dealing with simple capacitors over there. This stems from what's known as the parallel plate capacitor. Which I will often abbreviate as PVC.
That's what that typically is, but
Yeah, the symbol comes from the parallel plate capacitor, but even if it's not a parallel plate capacitor,
you'll still use
it's still that symbol.
Okay.
And a parallel plate capacitor is exactly as it sounds. You would take two plates that are conductors and you put them parallel to each other. And then if you hook it up to a circuit. So let's say that this is a 12-volt power supply. In other words, I don't know what the potential is at positive or the negative spot. Really don't. I do know that this one is 12 volts higher than that one. So this negative is 100 volts. This top one is, at the positive, is 112 volts. If I start at some particular point, because remember, let's think about when I introduce voltage. So let's say that's 1 volt, 2 volts, 3 volts. If I start here and go to here, what is my voltage? Going from here to here.
2.
Do the whole thing.
2 volts.
Yeah, there we go. If I start from 3 and I go to 1,
Negative 2 volts.
all right, so I got negative 2 volts. If I start here and I take some bizarre path, go through that one, and end up here,
Negative 2 volts.
yep.
-2.
So the path does not matter. So if I start at this point right here, at some voltage, or sorry, apologies, at some electric potential, and I move around and I go around and I come back exactly where I was, what is my voltage between this spot and itself?
Same.
Same.
Same as what?
Final and initial voltage are the same.
Therefore, what is,
Voltage
so the final and initial potential are the same. What is the voltage?
0.
0. Yes,
Okay.
volts. Now, if I have a circuit here and I start at this point and I go all the way around my circuit and I end up back where I started, what is the voltage between this spot and itself?
0.
Yeah. So when I go across here, I'm going to gain 12 volts because that's the potential difference between the two plates. So that means when I go across here, what's my voltage across here going in that direction?
Negative 12 volts.
Volts. And this in essence is known as Kirchhoff's voltage rule or loop rule. I think there are 2 H's in it. I could be wrong on that. So if I go around any loop, like if I add up all the potential gains and losses, I should have 0 at the end. So I have this parallel plate, and I know that the potential difference between the two plates is 12 volts. I'm going in that direction. Now, from a potential point of view, since I'm losing 12 volts as I move to the right, this has to be the lower potential than this side. Now, we know it's this side is negative and that side is positive. Well, let me reword that. This is the lower side, that's the higher side. I know that this right-hand plate is negatively charged. Because if I look at my power supply here, my power supply, I've got negative and positive here. I got this negative side, I got a bunch of electrons chomping at the bit to get away from each other. I attach something to it, and those electrons will finally push each other out, and those electrons will show up on this plate. So I'll get a charge here, and that charge there is going to drive an electron off of here, leaving behind a positive charge on this plate. Now, do note that the electron that gets onto this plate, the first electron that gets onto the plate is not the electron that comes out of the power supply. So let's get rid of some of this. If I have a long line, let's zoom in on the wire. This is hooked up to the power supply. And I've got a plate over here. I put the plate on it, and these electrons hit each other, so I'm going to get an electron onto here, which means I now have a hole. And now I have an electron fill that hole, creating another hole, and then I have an electron fill that hole, creating another hole. And then basically I have an electron traveling this way, and I have a hole traveling that way.
Sorry, Dr. Fox.
Yes.
That part of the white part of the screen is not view for me.
Ah. That,
Thank you.
okay. Now, this hole right here is not actually a particle, it's just a hole, but it's as if I have a positive charge moving off to the left. And I've seen some presentations where they talk about H+, this is just a hole. It's an illusion.
It's pretty much viewed as like a lack of an electron.
Yeah. Yeah. Now, the rate at which electrons are moving is on the order of centimeters per second. But it seems like the current is instantaneous because, well, all I care about is getting electrons onto this plate or moving. And electrons will start moving instantaneously, but an individual electron does not zip along the wire. It's moving along the wire at some calculatable rate. Now I do have two things that are moving here in a sense. I got the electron moving, and then I've got this illusion of a positive charge moving the other direction. But realize that when they were trying to figure all of this out, they did not know what was actually moving. Ben Franklin assumed that whatever was moving, this positive charge was moving. If you think about it, water flows downhill, and so some positive fluid, considered it a fluid at the time, this positive charged fluid moves down to a lower potential. And so he set up this convention that, well, I got something flowing this way. They call that a current. The symbol for it is an I.
Sorry, Dr. Fox. Would you mind moving the screen?
My beautiful description is not enough. My words are not like Shakespearean. So we have it set up so that the current in this situation is flowing clockwise, but closer to reality is we have electrons traveling in the other direction. Some textbooks get around this by calling it the electron current and the traditional current. I call it the current, and That's just the way the electrons are flowing. In high energy physics, you can get these long vacuum tubes and you do shoot positive particles through them. Protons are really nice to get. You can shoot protons through them, in which case the positive charges are, there is no electron current in that case. However, for the typical circuit, most of the stuff that you will deal with, what's traveling actually in the direction of current is the hole.
So current is the direction the holes travel.
Yeah.
Okay.
So officially, it's the direction of the positive charge flow, which would be opposite the negative charge flow.
Why don't they just make it the electron?
Because by the time they figured out that it was an electron, they said, we're not changing the convention.
So the flow of electrons is caused because of the creation of the holes?
What's that?
So is the flow of electrons caused by the creation of the holes, hence current?
In a sense, the electrons have to go somewhere.
Yeah.
I mean, they can't go to where another electron already is existing.
Mm-hmm.
I'll stick with that.
Are the holes, is that like a technical term? Is that? Or is that
It's-
just something you're using to explain it to us?
I have seen physics professors do presentations where they talk about the hole moving. They treat it like a positive particle flow. So the H plus is typically the symbol that they use for the hole. So, but it's really, as Raphael said, sort of absence of an electron.
Okay.
I can't remember if your textbook talks about the hole movement or not.
Yeah, because I was like explaining the concept of like the hole before, but they mentioned it more as like a positive charge along those lines.
There are a number of times in which you've got something negative flowing, and it's just easier to think about it, oh, I got negative charge flowing this way, let me just think about it as a positive charge flowing the other way. And there are times, most of the time, there's an exception, most of the time it is sufficient. The exception will show up in a couple of weeks. All right, so I have current flowing this way, and the current is going to flow until the capacitor fills up. At some point, because I keep getting electrons popping up here, and the more electrons I get on here, the harder it is to get another electron onto it, because now I've got this bigger repulsive force. If I got a big plate, then they're going to spread out, but if I've got a small plate, I can't get as many electrons onto it. So I'm playing around with these capacitors. I got my parallel plate capacitor, I got a positive, negative charge here. Which way is the electric field flow between the two? Going left or right?
Right.
The right.
Ideally, the electric field outside is 0. And we are assuming that the distance between these two plates, and I will make the assumption, if this distance here is d, d is much less than the length or the width of the plate. Not thickness being the other one. Length, width. Big dimensions. The magnitude of the electric field in between them, assuming that I can treat this, that D is very small compared to the size of the plate. Pretty sure we have done this one before.
What was the question?
the magnitude of the electric field between the two plates.
Is it just the area? No?
No, not just the area.
Is it twice, because both the electric field from the positive and the positive plate and the electric field from the negative plate?
Yeah, twice what? If I have an infinite plate with a uniform charge distribution on it, what is the electric field that comes from a single infinite plate with a uniform charge distribution? This is one of those things that's good to know. Infinite plate. And I'm some distance, so that's perpendicular to the plane, I'm some distance away from it, so from a side view it looks like this. The electric field at this point.
What is in the middle of the plate?
What, this right here?
Yes.
I was trying to indicate that this is not actually on the plate, that it's some distance away from the plate, and that distance
Oh,
right there is
okay.
perpendicular to the plate itself. That's what I was attempting. Where somebody knocked over a chair. So the magnitude of the electric field coming from an infinite plate.
It's in the area. Oh,
It is not related, the area of what I would actually then ask.
plate.
Plates are infinitely large. The electric field is not infinite.